Alright, we got this. Let's get it going. Open my notation package. Alright, let's get some line brackets. Total energy. Alright, generic subscript. Alright, and a generic superscript. Or a above script, I don't even know what you call that. Okay, well, let me go ahead and just a general clear notations. Let's do clear all global variables. Let's do that. Then let's do assumptions. Alright. Position, time, and total energy. Oh, come on. They are going to be elements of the reals, and my wave number, my initial wave number, my angular frequency, my reduced Planck's constant, my mass, my initial uncertainty and position, and I believe that's all those I would need. Just put some generic variables in there as well. Elements of the P reals. Alright, looking good. That's really all I need, but I'll go ahead and do N as the element of the non-negative integers. That looks good. Okay, let's get a wave function, initial time independent wave function. Sine of x. I'm going to do 1 over the fourth root of 2 pi times the square root of the initial uncertainty and position. Then we'll get a Gaussian amplitude e to the minus x squared over 4 times the initial uncertainty and position squared. Alright, then we'll get a plane wave function e to the I k. Oh, no, I just need I k. That's the initial wave number x position. Alright, now we'll get a Fourier transform going to get us to momentum space or wave number space. Yes, okay. This is going to be equal to 1 over the square root of 2 pi. Let's get an integral. Infinite boundaries. There we go. Let's get our wave function. Yep, looking good. And let's multiply that by e to the I k x. Let's do that. With respect to x, that's going to be what we need. Let me get a generic wave function so I can find omega. Okay, f of x t is e to the I kx minus omega k t. Alright, so our integral will work later. Now let's get a variable called freq, short for frequency. Let's solve our Hamiltonian equation. Alright, let's minus reduce Planck's constant squared over twice the mass times the second partial derivative with respect to position of our generic wave function, and this is going to equal I reduce Planck's constant times the time partial derivative of our wave function. And we are going to solve for the angular frequency with respect to the wave number. I know a part of the solution I'm going to need already, so I'll put that there. Alright, now let's get our time-dependent wave function, I need my underscores for defining a variable. So our inverse Fourier transform is going to look almost just like our Fourier transform. And you know what? On my Fourier transform, this is by convention we say negative. No, it doesn't really matter. I'll get the right answer, but we'll go ahead and keep convention. Alright. And we're going to take our infinite boundary interval again. Look, I need to put the right things in the right spot. There we go. That looks good. Alright, let's get our Fourier transform in this equation from momentum space or wave number space, and then multiply it by the generic wave with some of these, and with respect to k, and I'm going to insert my frequency, and let's see what will pop out. Alright, we have not evaluated the frequency. Let me see what answer I got for the frequency. Actually, that looks excellent. So why are we not evaluating at the moment? Let me see. Let me make sure that these are still looking good. Yeah, actually, symbolized looks great. Maybe I didn't hit it initially. Let's try it out. I know I got the warning up here, but that always comes up sometimes. It's thinking, so it might be working. It might be working. Yep. Yeah, I probably just forgot to evaluate these symbolized functions up top. Okay, that looks great actually. I haven't memorized that, but it looks good, so we're going to try to plot it real quick. Let's get something that we can plot. I'm going to need a function with all of my variables. So let's say capital psi of position, time. I'm going to have our initial wave number. Use a colon because of the subscript. Then what do we also have? We have reduced Planck's constant. We have the underscores. I need underscores on all of these. Yes, these still need underscores. Okay. We have mass, and then we also have the initial uncertainty of position. So we'll go ahead and put those, and I believe that's it. That's all my variables that I need. We'll set that equal to psi of xt. We'll call our manipulate function. We'll put a new function in xt k naught h bar m delta x naught. Alright, it looks good. Let's call some variables. Our time, we're going to go from 0 to 10. Let's go ahead and do animation running true. Then we'll do animation direction forward, backwards. Get a little front back action. There we go. Alright. Next we have the initial wave number. Let me give it an initial number, initial value. 1. I'm going to set these to 1. Let it go from 0.1 to 4. I think that's alright. Okay, let's try it. Actually, my reduced Planck's constant, I'm going to just set that to 1 because there's nothing spectacular about that. Mass, I can give it something. We'll start it at 1 and let it go from 0.1 to say 0.1 comma to say 10. Alright, that looks good. And then let's do one for our initial uncertainty and position. Again, we'll start it at 1. We'll just go from 0.1 to let's say 2. Let's try 4. Give some. Alright. I think that's everything. Let's see if this all plays out. Alright. Yep. X is my only variable. I got X here and X here. So that looks good. It looks exactly how it's supposed to be. If these change, let me stop this one real quick. These change, I don't have any other variables coming in, so I didn't forget anything. Alright, that looks good, so let me go ahead and plot this. Let's call it plot function. When I plot this, I'm going to plot the magnitude. The absolute value will give me the magnitude of a complex number. Then I'm also going to plot the real part. So that'll give me the envelope of the wave and the wave itself. But what did I do there? Oh, okay, no, I need to wrap this in the real. There we go. I wrap that in the real, and then let's close it. What did I forget? I forgot to close that one. That's fine. Let's call x from -5 to 15. Then let's give a plot range. So basically the y values. Plot range from, let's say 1. I go from -1 to 1. And that should be it. Let's look. Yep, perfect. Let's see. Is it moving? Oh, I missed it. Come on. Oh, look at that. Cooking with gas. Come on, let's. Oh, yeah, there we go. Increase our wave number. Increase. You see the frequency increases. That's actually right. We can decrease the mass. It actually gets faster. We increase the mass. It gets slower. All right. We can spread our wave function, or we can make it sharper. Yep. All right. That's it.